Hello, my name is Trent Moyer, and today I will be presenting on gait recognition using motion boundary histograms. Biometrics are individually defining characteristics that can be used in security applications. These are most notably used in smartphones to unlock them, such as Apple's use of Face ID in most of their phones, fingerprints becoming almost ubiquitous in the smartphone market, and more obscure example would be iris recognition in some of Samsung's phones. Another biometric that is seeing increased research that isn't used as much is the gait, or the way an individual walks. The previous state-of-the-art looked at the gait energy image, or the combined sequence of silhouettes of an individual's gait pattern, and then it could use this to identify the individual. This was quite good for more generalized tests, but when looking at cross-view analysis, where the probe and the gallery view were different, it failed substantially. Another avenue of gait recognition tried to use a model-based approach, where the joint positions were calculated using a tool such as OpenPose or AlphaPose, and then from that raw data, or extracting 3D data, the researcher could then identify an individual. This is a promising approach. However, the technology isn't quite there yet, with many pose estimation techniques requiring state-of-the-art GPUs, and even then they don't achieve incredibly high accuracy. One intriguing approach I found used motion boundary histograms. These look at the dense trajectories of an image, which are the trajectories calculated along certain points of an image, and then around those trajectories, it looks at the gradient of the optical flow. This provides a lower dimensional descriptor than the image itself of the movement within the image, while also accounting for camera movement, although the data set I will later be looking at does not have camera movement. However, each video has a different number of motion boundary histograms that can be extracted from it. This is difficult to use with machine learning, where needs to be a set dimensionality of the input and the output. So what the researchers did was find a Gaussian mixture model, which clusters the data into a probability distribution. And from this probability distribution, it can calculate the difference each video is from that distribution, which is then the Fisher vector encoding. And using this encoding, it can then insert it into the network. Rather than using a raw neural network, the researchers used a neural network and then a support vector machine. The first neural network encoded it into a canonical view, and then using this canonical view, it could then compare each one using a support vector machine. The problem with using a support vector machine is that support vector machines classify. They create hyperplanes to segment the data in order to classify them into different groups. In the case of the gait research, the groups would be the IDs of the individuals in the training data. However, if one were to use this research in the wild, where the training data, the data used is not the training data, these IDs would be inapplicable. So a different approach is needed, which is why I looked at using triplet loss and using only just a neural network and no support vector machine. Triplet loss takes the encodings of an anchor, a positive, and a negative, and tries to minimize the distance between the anchor and the positive while maximizing the distance between an anchor and a negative. In doing so, it can create an embedding that bunches similar gaits together, i.e. gaits of the same individual, and it moves gaits that are of different individuals further apart. This makes classifying the gait just a matter of comparing the distance between the embeddings. Before we look at the accuracy of my neural network, we first need to look at how we can identify the accuracy of a recognition algorithm, such as face recognition or gait recognition. Now, what that previous paper I mentioned likely used, and what other papers have used, is what is called the correct classification rate. This takes the number of correctly identified pairings and divides it by the total number of pairings. Now, the problem with this is it misconstrues those pairings that are where the gallery and the probe view are the same and those where the gallery and the probe view are different, as identifying whether a pair is the same and whether the pair is different can be two different tasks. As we can see, and that task can change depending on the threshold. In my case, the threshold is the distance. As with the previously mentioned triplet loss, identifying whether they're the same or not is a matter of finding the distance between embeddings. Now, if we look at this example here, where the orange represents identified pairings where the gallery and probe view are the same, and blue represents gallery and probe view where they are different, if we set the threshold here, we can see that those that are the same, which are the bright colored green and red, and those that are different have about the same accuracy. However, if we set the threshold here, those that are the same now has a much higher accuracy, but those that are different has a much lower accuracy. So even though the correct classification rate has stayed roughly the same, the model behaves much differently. And even if we set the threshold in a reasonable spot, if we test differently, where the number of tested negative gallery and probe view is much higher than those positive gallery and probe view, and the threshold is set here, we can see that the positive gallery and probe view achieves very low accuracy, almost 60%, while the negative achieves very high accuracy, and thus bumping up the correct classification rate, even though the accuracy of the model is not applicable in the field. Google's FaceNet saw this problem and introduced the validation rate and false accept rate. So for the validation rate, they look at the true accept, they take the number of true accepts, which are the same gallery and probe view that are correctly identified, and then they also look at the false accepts, which are the number of false gallery and probe view where the individual is different, but they were identified as the same. And it takes each of these and divides them by the number of same and number of different respectively. So validation rate is the true accepts divided by the same pairs, and false accept rate is the false accepts over the number of different pairs. And in doing this, we can set the false accept rate to be an arbitrary value, in my case 0.01. And in doing this, I can then identify my network and compare it to others who also set the false accept rate to be, in this case, 0.01. Looking at my model, we can see that it achieves subpar accuracy at a 0.01 false accept rate, achieving only 0.2 validation rate. And even then, that was at where the gallery and probe angle are the same, which is what those peaks are. And also the other data is almost insignificant in accuracy. However, if we compare it to the validation rate on the training data, we can see it's a much different picture, as the model likely overfitted on the training data, which even despite having a dropout of 0.5. And then if we were to compare it to the previous paper, that paper achieved almost what they claim to be 80% accuracy up here in the blue, and peaks nearly to 100 when the gallery and probe angle are the same. However, because they used the support vector machine, as I previously stated, their test data had to be on subjects that were used to train the model, which wouldn't apply in the real world. So it would be more fit to compare my training test to their test data. But regardless, there it still achieves much higher accuracy. What is next? I believe that gait recognition does have promise. However, it needs to see more maturity as a field. There needs to be more research into how we can identify models and their accuracy and compare the accuracy of models to find what truly is the best model. Also, the motion boundary histogram tool I used was somewhat inefficient, so another avenue of research would be into how we can speed up motion boundary histogram collection. And in this age of growing surveillance, it is important that researchers stay on their guard, that their research isn't used for nefarious means.